Welcome back to lecture series on aerospace propulsion. So, in the previous lecture, we are discussing about the combustion process happening in a gas turbine combustion chamber. What is the stoichiometric ratio and what is the equivalence ratio, and how do we find out the required amount of mass flow rate of air for the given fuel and all we have discussed in the previous lecture. Okay, so with that, the combustion chamber part is over. So today we are gonna start about the another important component of our gas turbine engine, which is basically nozzles. Okay, so as you know that the function of your nozzle is to produce the thrust force. Okay, so here before going to the nozzle section and all, first we are going to discuss something about the quasi one-dimensional flow and the one-dimensional flow, because your nozzle is basically it is the example for quasi one-dimensional flow. So we should know what is this quasi one-dimensional flow, how do they differ from the one-dimensional flow. Okay, so as you know what is one-dimensional flow, basically if the flow property variation is function of only one space coordinate, let's say it may be a x-axis or it may be y or it may be z. Okay, those type of flow what we call it as the quasi one-dimensional flow. Sorry, one-dimensional flow. In the one-dimensional flow, you will have a constant area duct. Okay, in which your flow property variation will happen along only one direction. That is the pure one-dimensional flow. Okay, now let's take what is this quasi one-dimensional flow. Quasi one-dimensional flow means here also you will have the flow property variation happening in only one direction, but the area will increase or decrease slightly. Okay, there is going to be a change in area. Okay, but what is the consequence of the change in area is that you will have V and W, that is you will have formation of three-dimensional flow, but thing is that you will have still flow will have only one major component. For example, if I'm going to say my flow is moving in the x direction, you will have u and v, v and w. But when we compare this v and w, they are going to be much smaller than u, or your u is going to be much greater than v and w. That is the quasi one-dimensional flow. Okay, and the change in, for example, if I'm going to take a passage, a cylindrical passage, okay, dr by dx is going to be much less than 1. Even though there is a change in area, the change is very gradual or very small. Okay, so when the flow is passing through this type of passage, what we call it as the quasi one-dimensional flow. Okay, so the best example for this quasi one-dimensional flow is that flow through nozzle or flow through diffuser. We can say it as a quasi one-dimensional flow. Okay, now so first, before say going to this nozzle section, we are going to derive a mathematical relation for a given passage. How does the same passage can act as a nozzle as well as a diffuser? In fluid mechanics and all, you might have seen, if I ask you to what is nozzle, you will just draw like this passage. You will say flow through this passage is going to be accelerated. You know what is nozzle, right? Basically, a passage which will accelerate your incoming flow, that is the nozzle. If a passage is going to decelerate the incoming flow, then that's what we call it as the diffuser. Okay, this diagram or this representation is only applicable for fluid mechanics, because in fluid mechanics basically we deal with the subsonic flow. Okay, so for the subsonic flows this is applicable, but when you take high speed aerodynamics, we have a subsonic as well as supersonic flow. So how a passage can act as a nozzle, how a passage can act as a diffuser, we are going to see by deriving this area velocity relation. From that we can explain this what is happening across a convergent passage if the flow is subsonic, what happens across a convergent passage if the flow is supersonic, and all we are going to see. Okay, so to derive this area velocity relation, I'm going to consider a stream tube. Okay, that is a quasi one-dimensional flow through a stream tube, in which my area, pressure, density, temperature, and velocity, all of them are function of x alone, and there is a slight increase in area as we move across in the x direction. Okay. So that's what the flow properties are uniform across any given cross section of the stream tube. Okay, so therefore the flow properties are function of x only, because we have taken or we have assumed that my flow is moving in the x direction, and this is only applicable for steady flow. Okay, that is a flow where your A is function of x, your P is function of, that is pressure is function of x, density is function of x, and velocity is function of x. Okay, for a steady flow, what we call it as the quasi one-dimensional flow. Okay, so as you know, for a one-dimensional flow, we have continuity equation from the conservation of mass, that is mass flow rate at any cross section. Okay, you take any cross section, the mass flow rate is going to remain constant. That is the conservation of mass. So since we have taken quasi one-dimensional flow, I'm going to write down the one-dimensional continuity equation, that is m dot a is equal to constant, or we have mass flow rate m dot is equal to density into area in cross-section area into velocity, which is equal to constant. Let's say this is equation number 1. Now I'm going to differentiate this continuity equation with respect to velocity v. Okay, so if I'm going to differentiate this equation, what I'll have, differentiation of d by dv of rho a v is going to be equal to 0, because here the other side is constant, you will have equal to 0. Okay, so I can split this. Okay, for example, I can group rho v as one term and a as one term. So if I'm going to differentiate this equation, you have to use the uv differentiation of d by dx of uv, right? So what is that? Uv dash plus v u dash. Okay, so here I'm going to take, let's say, u as rho into v and v as uh, capital A area. So what I'll have, uh, d by dv of rho av, I'll have uv dash. So rho v into dA by dv plus v u dash. V is your A and u dash is differentiation of d by dv of rho v, which is equal to 0. Okay, so in this portion is over. Now here we have once again rho v, the product of two terms. So once again we have to differentiate this. I'm going to take this term alone, this in the equation 2. This term alone I'm going to take, that is A into d by dv of rho v. So A is common, I'm going to keep as it is. If I'm going to differentiate, I'll have u v dash plus v u dash. So rho into dv by dv plus v into d rho by dv. So here this dv will be cancelled out, it will become 1. So A into differentiation of rho v with respect to dv is equal to A into rho plus v. So you'll have A into rho plus v into d rho by dv. We'll have d rho by dv. Okay, now what I'm going to do is that I'm going to multiply here and divide by dp. Multiply and divide by dp. So you'll have A into rho plus v d rho by dp plus dp by dv. So what I have done here, I have multiplied and divided by dp. So I have got this term. Let's say that is equation number 4. Now let's take a general form of our Bernoulli's equation. Okay, that is integration of dp by rho plus v square by 2 is equal to constant. So for the incompressible flow, we might have assumed that density is constant. So you will have p by rho plus v square by 2 is equal to constant. That is the Bernoulli's equation for incompressible flow. Here I'm taking a general form of my Bernoulli's. Okay. So if I'm going to differentiate this Bernoulli's equation, so what I'll have, differentiation of this will give me, what is that, v square, right? Differentiation of x square, d of x square is, what is that? It is 2x, that is nx over n minus 1, right? 2 minus 1. So here v square we have. So what I'll have 2v into dv, that 2 will be cancelled out. We will be left out with v into dv and a differentiation. Differentiation and integration will cancel out each other. You will be left out with dp by rho, which is equal to 0 because this side is constant. Differentiation will give you 0. So from this I can write uh, dp by rho is equal to minus v dv. So from that I can write dp by dv is equal to minus rho into v. Okay, and similarly from the Laplace equation, that is speed of sound, we have a is equal to root of dp by d rho. Okay, so you can write the speed of sound square, a square is equal to dp by d rho. Okay, so let's say that is equation number 7. So we have the value for dp by d rho and dp by dv. So here we have what? D rho by dp and dp by dv. In this place, I'm going to substitute these values. Okay, so when I substitute these values, what I'll get? A differentiation of rho v by dv is equal to a into, what is the equation we have? A into, we add this equation, a into rho plus d rho by dp and dp by dv. D rho by dp, dp by dv, right? So we got the value of dp by d rho. Okay, dp by d rho is a square dp by d rho into, so when we substitute this dp by dv and what is that? We have a into d by dv of rho v is equal to a into rho plus v into d rho by dp. Okay, so here when we substitute, what we will get? A is equal to rho plus v into 1 by a square into minus rho v, right? So this 1 by a square is what? 1 by a square is d rho by dp and dp by dv is minus rho v. So when we substitute, what I will get? We'll get v, if I'm going to take it inside, rho we have a constant. So a into rho, if I'm going to take it out, a into rho into 1 minus v square by a square. So what is this v square by a square? We have Mach number m is equal to v by a. So I can write it as m square. So a into d rho v by dv is equal to a rho into 1 minus m square. We have this equation number 8. This equation number 8 I am going to substitute in equation number 2. In the place of a into d rho v by dv is equal to, I'm going to substitute a rho into 1 minus m squared. So what we will get is that rho v into dA by dv plus a rho into 1 minus, this is m square, is equal to 0. Okay, so if I'm going to simplify this equation, that is, you'll have rho v into dA by dv is equal to minus of 1 minus m square into a into rho. Okay, so if I'm going to, you see here rho is common, so I can take it, it will become, if I am going to take it to the other side, it will become 0. You will have v into dA by dv is equal to minus a into 1 minus m square. So if I'm going to take this minus sign inside, we'll have v dA by dv is equal to uh, a into m square minus 1. So I can write this equation as dA by A is equal to dV by V into 1 minus m square, or you can write it as dA by dV is equal to minus A by V into 1 minus m square. This equation, what we call it as the area velocity relation. So from this equation only, we are going to see what happens, okay, if the Mach number is subsonic, and what happens if the Mach number is supersonic, and corresponding to which, that is, if the change in area is positive, what will happen to the change in velocity? The change in area is negative, what will happen to the change in velocity? That's what we are going to see in the next section. Okay, this is a area velocity relation. Now, let's say for the incompressible flow. So what is incompressible flow? We'll say for flow which is Mach number less than 0.3, we usually call it as incompressible flow. But mathematical limit for the incompressible flow is m is equal to 0. Okay. So in this equation, if I'm going to substitute m is equal to 0, what I'll have? dA, okay, by dV is equal to 0. So which is basically, if I'm going to integrate it, what I'll get? A into B is equal to constant. What is that? For the incompressible limit, once again you are going to get the continuity equation, right? Rho AV is constant, right? That is the continuity equation for the incompressible flow. Okay. So now, if I'm going to take Mach number greater than 0 and less than 1. What is Mach number greater than 0 and less than 1? Basically, it is subsonic flow. Okay, let's take a subsonic flow. We have an equation dA by A is equal to dV by V into m square minus 1. Okay, so if you take a subsonic flow, what is happening? Here, if I'm going to substitute less than 1 means this term will become negative. Okay, so what does that mean? You'll have dA by A is equal to minus dV by V. So what is this equation state is that for an increase in area, for the subsonic entry, the increase in area, that is, increase in area means positive change in area will result in negative change in velocity. Negative change in velocity means velocity will decrease. Okay, suppose if the area is decreasing means, okay, this is basically negative sign, minus and minus will become plus. Area decreases means your velocity will increases. So what does this equation state is that, suppose if I'm going to take a convergent passage and a divergent passage. So what is happening to this convergent passage? Your dA is decreasing, that means it is negative. So your flow is less than 1, basically subsonic. So what does this equation state is that for the negative change in area, that is for the convergent section, if the subsonic flow enters means positive change in velocity will happen, that is your flow will be accelerated. For the subsonic flow, a convergent section will act as a nozzle. Now, let's take a divergent passage where your area change is positive, that is, area is increasing. So, we have seen for the positive change in area, the change in velocity is negative. So, your velocity is going to be decreased. A divergent passage will act as a diffuser for the subsonic entry. Okay, so as you can see here, convergent section will act as a nozzle for the subsonic entry, and divergent section will act as a diffuser for the subsonic entry. Now, let's take my Mach number is greater than 1. So, we have dA by A is equal to dV by V is equal to m square minus 1. Okay, so what is this m is greater than 1? Basically, it is a supersonic flow. Okay, for supersonic flow, m is greater than 1 means this is positive. So, what is that? You are getting dA by A is equal to dV by V. That is, for a positive change in area, your velocity will be positive. For a negative change in area, your velocity will be negative. That is, in sense, the area increases means your velocity will increase. Area decreases means your velocity will decrease. So let's take a convergent section. under divergence section. If the Mach number is greater than 1, for the convergence section, what is happening to your area? Your area is decreasing. So change in area is basically negative. So your velocity will decrease. For supersonic entry, the convergence section will act as a diffuser. Okay. Whereas in the divergence section, what is happening? Your area is increasing, so your velocity will increase. For the Mach number greater than 1, a divergence section will act as a nozzle, that is, flow will be accelerated. Okay, as you can see here, for same convergence section will act as a nozzle for subsonic entry, will act as a diffuser for the supersonic entry. So you can see the passage, whether it is going to accelerate or decelerate, depends on the incoming Mach number. So if it's subsonic, it will behave differently. If it is supersonic, it will behave differently. Okay. So this is what for, let's say, if I'm going to substitute m is equal to 1 in this equation, what I'll have, we'll have dA by A is equal to 0. What does this means? Basically, the area at the location where m equal to 1 is going to be either minimum or maximum. Okay. So what does it mean? This dA by A is equal to 0. Mathematically, it represents at that particular location, it is going to be either minima or maxima. Okay. So what this is dA by A is equal to 0 for m is equal to 1 state is that in a passage where your m is going to be 1 is going to be either at the location where your area is minimum or your area is going to be maximum. But if you take a convergent nozzle, okay, the Mach number 1 will happen at the exit location, basically at the minimum area location. So you can say, if you take either convergent section or convergent divergent section, the Mach number 1 will happen at the minimum area location. So for the convergent divergent section, at the throat location, your Mach number will achieve 1. Whereas for the convergent nozzle, your Mach number will reach 1 at the throat location. Okay. So that's what the minimum area location only you will have the Mach number is equal to 1. So basically this is the schematic of, like, for example, for the subsonic entry, convergence section, what will happen to velocity? Velocity will increase. Okay. And divergence section, the velocity will be increased. Whereas for the divergence section, subsonic entry means velocity will decrease. For the convergence section, supersonic entry means your velocity will decrease. Okay. So, and one more thing is that here from this one more observation we can make is that, you see, I said, like, at the minimum area location, you will have m is equal to 1. That means if I'm going to take a convergent nozzle, the maximum Mach number this convergent nozzle can produce is m is equal to 1. It is sonic Mach number. If at all you want a supersonic Mach number, you should go with the convergent divergent nozzle, because convergent nozzle alone won't be able to produce the supersonic flow. It will maximum produce is sonic Mach number, m is equal to 1. So if you want supersonic flow means you should go with the convergent divergent nozzle. Okay. So with this, I'll end this today's lecture. Okay, so what we have seen? We have seen the what is one-dimensional flow and what is quasi one-dimensional flow. Flow through nozzle or flow through diffusion, basically it is the example of quasi one-dimensional flow. And we have taken a quasi one-dimensional flow through a stream tube. From that, we derived the equation, that is area velocity relation, dA by A is equal to dV by V into m square minus 1. For this, we have seen for the different Mach number entry, what will happen. For subsonic entry, we have seen the positive change in area will create negative change in velocity. Okay, negative change in area will create positive change in velocity. Whereas for the supersonic, positive change in area will create positive change in velocity. Negative change in area will create negative change in velocity. That is, for supersonic, if the area increases, velocity will increase. If the area decreases, velocity will decrease. Whereas for the subsonic entry, area increases means velocity will decrease. Okay. If the area decreases means velocity will increase. And one more thing we are saying, the Mach number m is equal to 1 will be attained at the minimum area location of an passage. If you take any passage, in the passage, if at all there is going to be a Mach number m is equal to 1 achieved means definitely it will be at the location where your area is minimum. Okay.
Like, share and subscribe. Hit the bell icon for more updates.